Jump straight into the second half, and I think we may finish a little early today, which would be great. When we do probability calculations, especially for equally likely probabilities, we often need to think through how many different possibilities are there. And so for that, we need to have the ideas of some counting techniques, some counting rules. One of those rules we saw earlier when we talked about rolling 2 dice. If those 2 rolls are independent, and there's 6 outcomes for the first and 6 outcomes for the second, then the total number of outcomes between them is 6 times 6. That's a multiplication rule. Okay. So one of the things we can use to help us calculate these things quickly is a factorial. Hopefully you've seen a factorial before, maybe you haven't. It looks just like an exclamation point. Right? But when you see a number followed by an exclamation point, this number, at least in this class, it should be a positive integer. What it means is start with that number and multiply it by the next number down, the number before that, the number before that, all the way down to 1. So for instance, if I wanted to calculate 3 factorial, that would be 3 times 2 times 1. Similarly, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And notice, 3 factorial is a divisor of 7 factorial. It's actually part of the 7 factorial calculation. Right? Those things are important. We'll actually see that come up in just a moment. Now, what are factorials good for? It turns out they are a great way to understand how many different ways you can rearrange a set. Right? If I had 4 students in 4 seats in front of me, and I wanted to know how many different ways could I rearrange them, I could rearrange them in 4 factorial ways. The reason is, if I pick the first seat, how many students are possible for that first seat? Let's actually do this on the document cam here. So if I have 4 seats, and let's say I have students A, B, C, and D, how many possibilities are there here for the first seat?
4.
4. Let's say I chose student B. Okay? This is just one example. Once I've chosen student B, that person is already seated. How many choices are there for the next seat?
3.
3. All right, could be A, C, or D. Let's say it's D. All right, well, that person's already seated. How many choices do I have for the third seat?
2.
2. And how many choices for the first seat?
1.
All right, this is just one example. Obviously, I could have chosen a different number here, come up with a different list. If I list out all the possibilities for the orderings here, how many will there be? It'll be 24. All right, 24 ways I can rearrange those 4 students in order. Factorials are nice in that sense. They give us a quick way to see how many ways we can rearrange that idea. I'm going to stay on the document cam and show you an interesting question. How many ways can I rearrange the letters in this word?
About the same. 4 times 3 times 2 times 1.
All right, I have 4 letters to choose from. I can rearrange them by picking one letter first. Then there's 3 more to choose. And then there's 2 more to choose. And then there's 1 that's determined at that point. And so the answer is, again, 4 factorial, which is 24. If I give you a more complicated word, you could use the same ideas, but you have to be careful. What about that word?
The T appears twice, so it's going to throw a curveball.
Yeah. The fact that there's 2 T's makes it a little complicated. How do we handle that? Here's the neat thing. We can use that same double count idea, but now it's in a multiplication question. right? If I assumed that this t and this t were different, how many possibilities would there be?
24.
Yeah, the 4 factorial, right? But because they aren't, what I can do is I can say, suppose I picked a particular way of ordering it. Maybe it was STTA. How many ways could I rearrange that and have exactly the same letters? Well, I could swap the t's, right? That means like this word in particular, stat, will be counted twice in my list. Once with this t first, and once with this t first. I can get rid of that overcount by dividing by 2. Technically 2 factorial because there's 2 ways to rearrange those t's. Okay. Well, let's try the same idea. What if I want to rearrange stats? Now there's 2 letters that are repeated, the t's and the s's. But we can count it the same way. We start with how many rearrangements of 5 letters are there? Take a stab at it.
Would you start with 5 times 4 times 3 times 2 times 1 just to get a base?
Exactly. 5 factorial. If it helps, that's 120. And we know it's going to be less than that because there's some repeated letters, right? So let's do the letters one at a time. How many s's are there?
2.
And how many ways are there to rearrange those 2 s's in the same word? Yeah, 2 ways. What about the t's?
2.
There's 2. And that's it. That's all the repeats. So when I put that together, there are 30 ways to rearrange the word stats in a unique order. I'll leave it to you to do that on your own time. I don't want to do that in front of you here, but we could do that, and we would find there are exactly 30 ways to do this. Now, one of the fun ones I was asked years ago, I grew up in Tennessee. A lot of repeated letters there, but there's even more in Mississippi. How many ways can I rearrange the letters in Mississippi into a unique word?
A lot.
A lot, that's true, but we can be more specific. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 letters, so we're going to start with 11 factorial. Okay. But then we need to account for those repeats. Now, which letters are repeated?
I.
Right.
S.
I, S, and P. Let's start with the I. How many I's are there?
9.
Looks like 4. And there's 4 factorial ways to rearrange those I's inside of the same word. Right? If the word is literally Mississippi, it's been written in that order, I have 4 factorial ways to swap these I's around and still have it spell out Mississippi correctly. So if I divide by 4 factorial, that accounts for reordering those I's. What about the S's?
4 once again.
Yeah, there's 4 S's, and so there's 4 factorial ways to rearrange those inside of the same order. Okay. Lastly, how many P's?
2.
2. And there's 2 factorial, which is just 2 ways to rearrange the 2 P's. If I put all that together, that will give me the number of ways to rearrange the letters in Mississippi to form a unique word. Right? Again, listing that out would be a serious pain, but I will show you how to calculate the product, and I want to show you some cancellation that happens here because that's useful. This technically times a 1 there. All right, so what can I do here? Well, this 4 factorial shows up as these last 4 numbers. So rather than multiplying all of this out, I can go ahead and cancel some of those. Okay. What else? Well, I know that 4 times 2 is 8. And I know that 3 times 2 is 6. So all I have to do is multiply those 5 numbers together, and that tells me how many ways I can rearrange the letters in Mississippi. Okay. I did not do this beforehand. I'm not going to do this right here in front of you. Then I'll make a mistake, and it'll be preserved in the video. Don't want to do that. So I'll leave it to you to multiply those together, but this is the idea. This is how it can be calculated. I will show you more in just a moment, but I wanted to show you how factorials work and how you can use them, to understand rearrangements, and also to simplify the calculations involving involving factorials. Okay, with the punchline, on the next slide now, we're going to talk about permutations, which are a particular way of thinking about ordering sets. All right. So you may have seen this notation before. If you have, great. If you haven't, that's okay. Permutations are essentially the idea we were just using. Suppose I have a collection of n objects, and I'm going to select some smaller number of them and consider the order of them, right? How many 3-letter words, for instance, can I form from a 26-letter alphabet? In order to do something like that, I need to use permutations. Okay, I'll show you that particular example in just a moment. But the idea is I have a fixed collection I'm starting with. I'm selecting some smaller set, some smaller collection from that group. And I also care about the order in which they're listed, okay, the order in which they're selected. That's when you use a permutation. It's often summarized as order matters. Okay? So the first example I want us to do is 3-letter words from a 26-letter alphabet. I'll show you this in just a moment. And the second example is license plate numbers that are 6 characters long, the first 3 being uppercase letters, and the, why did I say uppercase numbers? That's funny. And the next 3 are numbers, right? All numbers are uppercase numbers in my world. We'll call it that. But I don't want repeats. Okay. So how can I do that? Well, let's put this stuff together. We'll go over to the document cam one more time. All right. So if I want 3-letter words, so I'm going to do 4-letter words as a nice example with better numbers, but then I thought that would be loaded. So we're going to go with 3-letter words from a 26-letter alphabet, right? I had one in particular in mind, but we'll leave it at that. 3-letter words out of a 26-letter alphabet. If I didn't know permutations, right, how would I calculate that? Well, I would use the same organizing principles I used before when I tried rearranging the letters or rearranging the students. I'm going to make a 3-letter word without repetition. How many letters can I choose for the first letter?
26.
26. All right, now I've chosen that one letter, whatever it is. How many choices do I have left for the second letter?
25.
25. And then lastly, how many choices for the third letter?
24.
24. So if I multiply those things together, that should give me the total number of possibilities here. Okay. Now I claim that that is the permutation of 26 and 30. That's 26 factorial divided by 26 minus 3 factorial. Calculate that out really quickly. Now, if you remember what we saw on the previous, not slide, but sheet, this 26 factorial is 26 times 25 times 24 times 23 factorial. Okay. Apologize for the notation there, it's hard to see. And the reason why hanging it that way helps me is there's a 23 factorial here that I can cancel with the 23 factorial in the numerator. And what's left is 26 times 25 times 24. That's exactly the approach we found up here. Okay? I didn't multiply those out here, but on my slides it says that it is 15,600. You definitely don't want to list out all those possible words. It would take forever. But it's easy to see that that's the total number of words. I can make this a really difficult problem and ask how many of them are actually words in the English language, but I'm not going to do that. Okay? I know there's no more than 15,600 words in the English language that are of length 3. I can think of a few that are not words. Okay. Well, let's try the second question. How many license plate numbers are possible if the license plate has to consist of 3 letters, 3 uppercase letters, followed by 3 what I called uppercase, but just numbers. Okay. And I don't want any letters or numbers to be repeated. Alright, well let's go through this. How many possibilities are there for the 3 letters?
Would it be the 26, 25, and 24 again?
Right. You could think of those 3 letters as a 3-letter word. We just calculated that. It's going to be this 15,600. I'll write it this way just so you can see where it comes from. So it's going to be 26 from unit 3. All right. Well, what about the numbers? If I don't want any numbers repeated, how many numbers are possible here?
9.
So there's 10 digits in the first case, right? Anything between 0 and 9. What about the second one?
9.
Yeah, once I've made that first choice, there's 9 left over. And then for the last one,
8.
8. So the best way to think about that is I have 10 digits to start with, and I'm going to pick 3 of them. And of course, the order does matter. That's what this notation means. And then finally, if I want to pair those things together, I have a 3-letter word and a 3-digit number. The total number of possibilities is just multiplying those 2 things together. Okay. So let's see, this was 15,600 we saw a moment ago. And this is going to be 10 times 9 times 8, which I guess 9 times 8 is 72, times 10 is 720. I think I have the answer on the slides here. Yes, I do. 11,232,000. That's a lot of license plates. All right, questions about that? That's permutations.
Yeah, actually, if you don't mind, when you did the first example, when you did the 26 permeation of 3, or 26 with, yeah, why did you add the 23 at the bottom part when there's only 3 permeations of 26, 25, 24? Why did you add the 23 to that? Do you see what I mean?
Why is
Yeah,
it
right
one
here.
factorial here?
Well, right underneath it, that fraction where you took the 23 out of the bottom and the top, if there was only 3, why did you add the 23 to the top number of
Okay.
that?
So the formula that permutations use looks like this. It's n factorial divided by n minus r factorial. And really what it's doing is it's saying, I only want the first r numbers in this factorial. Right? So here I want just the first 3 numbers in the calculation of 26 factorial. If I divide by 23 factorial, it cancels out the last 23 numbers. So that's why this works. Okay? This is the easier way to see it directly. Just take those 3 numbers and multiply them together. But if I write it in terms of factorials, I can multiply all of the numbers and then divide out the last 23. So that what I'm left with is 26, 25, and 24. Does that explain it?
Yeah.
This notation is going to seem tedious. It's actually very useful for a calculator to be able to use it, and it's also useful to know how you can combine multiple things together. So for instance, the example with the license plate numbers, if you haven't seen permutations before, it's complicated to see what to do with those 3 separate calculations. But permutations make the first 2 easy, and then once you know what a 3-letter word and a 3-digit number are separately, you can multiply them together to get the total number of possibilities. And that's, again, that same multiplication counting rule. The thing to emphasize, when I use permutations, the order matters. So like for a 3-letter word, the word THE and the word HET are different. Same 3 letters, different order, it's a different word. Order matters, so that's why I use the permutation. But what if I'm in a situation where order doesn't matter? So let's go back to the slides. That's where combinations come in. Combinations are how many unordered subsets. Let's say the subset is of size R, and the set I'm drawing from is size N. So here I might be saying, I'm going to pick names out of a hat. I have 10 names to choose from, and I'm going to pick 3 of those names. How many possible trios are there? Well, that's where I would use combination 10, 3. Okay? And if you look carefully, you'll notice the n factorial and n minus r factorial from permutations are already there. The difference is I have this extra r factorial in the denominator. Why is that? Well, once I choose an ordered list of 3 people, there's r factorial different ways I could have gotten that same list. So if I divide by r factorial, I'm removing the requirement that the order matters. I'm getting rid of the overcount when I do that. So that's what that does for me. Combinations are actually useful for a lot of things. If you've done FOIL as an algorithm for multiplying polynomials, you know that there are 4 different terms to consider when you multiply a binomial by a binomial, right? And we also learned special that if I take x plus y squared, it's x squared plus 2xy plus y squared. Well, that's a simple case of what's called the binomial theorem. If I did x plus y to the 5th, I can actually use numbers like this to think about how many copies of x and how many copies of y are in each term, and it gives me a quick way to find those coefficients. That's also why the theorem that tells us how to do that is called the binomial theorem. And later in this course, we'll learn about a binomial distribution, which is built on the same things. Okay. So when you see this notation, this is the notation I will usually use for combinations, but this is the one that parallels the previous notation. It's thought of as n choose r. And what that means is, how many ways can I choose r different objects out of a group of n, where the order doesn't matter? So if I'm picking 3 numbers out of my collection of 1, 2, 3, 4, and 5, how many different possibilities are there? Well, if there's 5 possibilities, it means I'm going to start with 5 choices to work with. I'm going to pick a subset of size 3. So what I want to calculate is 5 choose 3, or the notation I like to use is this. If I start with a group of 5 students and I'm going to pick 3 to present their homework today, how many different ways can I choose that group of 3? It'd be 5 choose 3. And what does that amount to as a calculation? Well, it's 5 factorial over 3 factorial and 2 factorial. So in this case, that's 5 times 4 over 2, or 10. There are going to be 10 different possibilities for the trio of students I have present if I'm taking 3 out of a group of 5. This is really useful for card deal probabilities. So for instance, if you want to find the probability of a hand in poker, you can use this exact idea. All right? But suppose I'm playing 5 card stud. Okay, so I get 5 cards in my hand. There's no draws. I just want to see how many possible hands are there. How many possible 5 card hands? Okay. How many cards are there in a standard deck?
$52.
Right. So I'm drawing from a collection of 52 cards. How many cards am I drawing?
5.
All right. And the number of possible hands is just 52 choose 5. Okay, so this is a nice way to note that. That's 52. That's 51. That's 50. That's 49. That's 48 over 5 factorial. I should have written this a different way. Let me show this first. 52 factorial over 5 factorial. That's 47 factorial. This is the r factorial and n minus r factorial. But when I look at this, the 47 factorial cancels out everything from 47 on. And that's why I have 52, 51, 50, 49, and 48 that remain. And then this other 5 factorial is still there. Now 5 factorial is 5 times 10 times 12. So I can reduce this and find the exact number of hands that are possible. I didn't do that. All right, so let's return back to this example. So suppose I'm drawing out of my set of 5, I'll write those down again. I'm drawing 3. Okay. Then the probability was C of 5 comma 3. Or excuse me, the number C of 5 comma 3 was 10. There were 10 possibilities. How many subsets are there of size 2, or size at most 2? How many subsets of size less than or equal to 2? How could I calculate that? It probably helps to think about what it means to be a size less than or equal to 2. It means it could be a size 2, could be a size 1, or technically it could be a size 0. Okay? Each of those are possibilities. So let's see. And then when I put those together, I can just add them to get the number of subsets of size less than or equal to 2. So, how many subsets are there of size 2? Well, I have 5 elements to choose from, and I'm picking exactly 2 of them. So that's 5 choose 2. Now, if you multiplied all of that out, 5 factorial over 2 factorial, 3 factorial, that'd be 120 over 2 times 6, which is 120 over 12. So that's also 10. It's not hard to see why these two things are the same, right? Because if I were to pick a set of size 3, the ones I didn't pick would be a set of size 2. So those two things should be an equivalent number, right? Every time I pick a set of size 3, there's a set of size 2 that I didn't pick, and vice versa. So that's why those counts would be the same. How many sets are there of size 1? Well, intuitively, 1, 2, 3, 4, 5, there's 5 sets of size 1 that I could choose. If I use this notation, it's 5 choose 1, and that's 120 over 24, which does amount to 5. Now lastly, this is one I'm just going to have to define for you, because what this is this expression. Now the 5 factorials will cancel. And I haven't told you yet, but we defined 0 factorial to be 1. Okay? That's because we set this to be 1. How many ways are there to arrange no objects? Well, however the no objects are arranged, we treat that as the only way. Technically, it comes from the fact that the way this interacts with everything else requires it to be 1 for this to work. All right. And so what is the total? How many subsets of size at most 2? Well, there's 10 that are exactly 2, there's 5 of size 1, and 1 that is empty. And that would be 10 plus 5 plus 1, 16. So there's 16 subsets of size at most 2. All right, I think that's where I'm going to stop today. I don't want to go too much further. I suppose just for fun, I will show you how you can calculate these to find, for instance, a particular poker probability. Let's see. One of the better hands in poker is a 4 of a kind. Okay? And what that would be is 4 of the same number, like 4 sevens, or 4 jacks, or 4 aces. Okay? So if I asked you how many different 4 of a kind hands are possible, well, this is how you would organize your thinking. All right, let me write that down. Let's say it's a 5-card hand. Okay. Well, here's what I can do. I'm going to organize my thinking by saying, first, which kind? That is it a 2, an ace, or something else? Okay. Once I've picked which kind it is, I need 4 of them. And then lastly, I'll figure out how many other cards. Could be in my hand. Okay. When I put these 3 pieces together, I can actually calculate the probability of any poker hand. It's a little more complicated when I do 3 of a kind because I have to make sure to remove the situation where I have 4 of a kind. If I have 4 of a kind, I do have 3 as well, but we don't usually call that 3 of a kind. We stick with the better hand, 4 of a kind. So that makes it a little complicated. But this hand is unique. I'm not going to see 5 of a kind, so that's okay. All right, so let's see. How many kinds are there in a standard deck of cards? That is, if I took ace, 2, 3, 4, all the way up to king. How many different kinds could there be? Yeah, there's 13 kinds, and there's 4 of each kind, right? There's diamonds, hearts, spades, and clubs. So there's 13 kinds. I'm going to pick one of those to be the kind that I have 4 of. Right? Maybe it's jacks. Okay? There's 13 possibilities. Jacks is just one of them. Once I've picked which kind, how many of that kind are there?
4.
Right, so if it's jacks, there's 4 jacks to choose from. How many do I need in my hand to have 4 of a kind? 4. All right. How many other cards are in my hand?
1.
1 card. And that 1 card could be any of the remaining 48. This is the number of 4 of a kind hands if I multiply these 3 numbers together. Okay. This is a neat feature that combinations, 13 combination 1, 13 choose 1 is always 13. 7 choose 1 is 7. 52 choose 1 is 52. Just always works that way. So that's 13. How many ways are there to choose 4 objects from a group of 4?
16.
Nope. In order to choose all 4 objects, there's only one way. I take them all.
Oh, right. Okay.
That's all it comes down to. If you use the calculation, it's 4 factorial over 4 factorial. And that's why it cancels out. There is actually also a 0 factorial in there, but that's why 0 factorial has to be 1. It makes that work out. And then 48 choose 1. How many ways are there to choose 1 card out of 48? There's 48 of them. 13 times 48 is how many 4 of a kind hands there are. If I wanted to make that into a probability, I could divide it by 52 choose 5. And if you look up on any website what the probability of 4 of a kind is, it will be this number over the number that is 52 choose 5.